chemical shifts. When we want to take the NMR spectrum of the sample, a small amount of an inert reference compound is generally added to the sample tube containing the sample. And the most commonly used reference compound is tetramethylserine, also called as TMS. Because it is highly volatile, having a boiling point of 26.5 degrees Celsius, it can be easily evaporated after the experiment is done. The methyl groups which are present in tetramethylserine are said to be in a highly electron-rich environment because silicon is less electronegative than carbon. And therefore, all of these hydrogens, these methyl hydrogens, are said to be shielded, and they are going to have the protons existing at lower frequency in the NMR spectrum. The position at which a signal appears in an NMR spectrum is called as the chemical shift. And it is basically a measure of how far the signal is from the signal for the reference compound, basically TMS. Now, the most commonly used scale for chemical shift is delta scale. And in the delta scale, the methyl group in the TMS is going to be assigned a value of 0 ppm. The chemical shift in delta scale is generally determined by measuring the distance from the TMS peak in Hertz divided by the operating frequency of the spectrometer in megahertz. Now, one of the greatest advantages of using the delta scale is that it is independent of the operating frequency of the NMR spectrometer. Because when you take a look into these units right here, so it is Hertz over megahertz, which can be rewritten as Hertz over 10 to the power 6 Hertz. So this is basically nothing but 10 to the power of minus 6, which can be represented as ppm. So the delta scale is conveniently represented in ppm. In HNMR, the protons can come anywhere between 0 to 12 ppm, and in carbon-13 NMR, the carbons can come anywhere between 0 and 220 ppm. Here is the NMR spectrum of a compound which has got two signals. There is a signal at 1.05 ppm, and there is also a signal at 3.28 ppm. Now, whether you take the NMR spectrum in a 300 megahertz spectrometer or in 500 megahertz spectrometer, these values are going to be the same if you're going to use the delta scale. And you don't have to specify the operating frequency of the spectrometer if you're going to use the delta scale. But let's say that you're going to report the chemical shift values in Hertz, then you have to specify the operating frequency of the spectrometer. Let's say that you're going to use a 300 megahertz spectrometer. This 1.5 ppm is going to correspond to 315 hertz. Then in that case, this should be written as 315 over 300, or it should be written as 315 hertz in a 300 megahertz spectrometer. So you have to specify the operating frequency of the spectrometer when you're not going to use the delta scale. So here is a summary of all that we have talked about in this video and in the videos before. Protons that are said to be in electron-poor environments are said to be de-shielded, and therefore they are going to appear in the downfield region of the NMR spectrum, and they are going to take more energy to come into resonance, and therefore they are going to have larger delta values. Whereas the protons that are said to be in electron-rich environment or electron-dense environments are said to be shielded, and therefore they are going to appear in the upfield region of the NMR spectrum, and they only require very low energy or low frequency to come into resonance, and they are going to have smaller delta values. Let's now take an example to determine the relative positions of the signals for the protons in a set of 4 different compounds, 4 different alkyl halides. Now here are 4 different alkyl halides, and the only difference between these 4 compounds is the presence of the halogen. So here you have fluorine, chlorine, bromine, and iodine. Now when you compare the electronegativities of fluorine and iodine, we definitely know that the fluorine is the one which is more electronegative. And because the fluorine is more electronegative, these hydrogens, these methylene hydrogens, are said to be de-shielded. And therefore they are going to appear at a higher frequency or higher delta value. On the other hand, these hydrogens which are closer to the eye are said to be in a shielded environment, and therefore they are going to appear in the lower frequency region, so lower delta value. So when you take a look into the actual ppm values for these compounds, it can be clearly seen that as you go from fluorine to iron, you can see that the delta ppm values is constantly decreasing, and that is because of the decreased electronegativity of the halogens in this order. Here is a table that provides the chemical shift values for some of the protons. So you can see that methyl protons are going to come somewhere around 0.85 ppm, while the methylene protons and the methane protons are going to be relatively downfield and comes at 1.2 and 1.55 ppm respectively. And the ethers are going to come somewhere around 3.3. And when you have benzene, when you have hydrogens in the benzene ring, that's going to come somewhere between 6.5 and 8. Basically, aromatic protons are going to come in this region. When you have amines and hydroxyl groups, then the hydrogens that's present in the NH2 and the OH are going to be variable. And in the case of amines, the hydrogen can come anywhere between 1.5 and 4. And for the hydroxyl group, the hydrogen can be between 2 and 5. For aldehydes, the hydrogen is going to be relatively downfield between 9 and existing between 9 and 10 ppm. And for carboxylic acid, the hydrogen in carboxylic acid is also going to be variable, and it is also going to be in the downfield region anywhere between 10 and 12. And again, similarly for the amide, the signal for hydrogen is going to be variable, existing somewhere between 5 and 8. But keep in mind, these are not the exact values. The values can fluctuate depending upon the neighboring substituents present. You have to make sure that you know the rough values of all of these different types of protons. It is definitely important that you know at least the tentative values for these different types of protons in the NMR spectrum. Why should the methyl protons, methylene protons, and methane protons have different chemical shift? In order to answer this question, we needed to look into the electronegativity of carbon and hydrogen. Carbon has an electronegativity of 2.5, and for hydrogen, it is 2.1. And as you can see from the structure here, as you go from right to left of these structures, you can see the number of carbons is actually increasing. Now here, let's take a look into this. This hydrogen is connected to a carbon, which in turn is connected to one carbon, right? So the electronegativity is going to be less because there is only one carbon. But here, there are two carbons, and in here, there are three carbons. With three carbons, the electronegativity is going to be more, right? And because of which these hydrogens are said to be in an electron poor environment. So this is in an electron poor environment because of the electronegativity of three carbons, whereas these hydrogens are in an comparatively electron rich environment, right? And because of which this is going to be shielded, and therefore it's going to take lesser energy to come into resonance, whereas this one is going to take more energy to come into resonance because this is de-shielded. Okay, and therefore you can definitely see this from the values here. So this is the de-shielded proton, while this is the shielded protons exhibiting a lower frequency signal. In the same environment, the chemical shifts of the methane protons, methylene protons, and the methyl protons are going to be following the same order, where the methane protons are going to be in the downfield region, and the methylene protons are going to come in between, and then finally the methyl protons are going to be in the upfield region, right? So this is going to be the order of the chemical shifts. Now let's do this with an example. Let's take butanone. In butanone, we have two CH3s, right? So between these two CH3s, which one is going to be in the far upfield region? Obviously, it is going to be this one because this CH3 is closer to the electron withdrawing group. This is a carbonyl group, and a carbonyl group is said to be an electron withdrawing group, right? So these hydrogens are the one which is going to be in the upfield region, and then it would be this. Remember that when it comes to methylene protons and the methyl protons, it is the methyl protons which is going to be in the upfield region. Now, after these methyl protons, it would be the methylene protons. Here, the protons are designated alphabets A, B, C, with the A being the one which is going to come in the most upfield region, and B would be the next, and so on. And the methylene protons are going to be in the relatively downfield region. So it has been assigned C. Now let's go on to the next example. Here we have 2-methoxypropane. So in 2-methoxypropane, we have 3 CH3s. Out of these 3 CH3s, these 2 CH3s are going to be in the same chemical environment because they are both connected to the same carbon. And they can be designated as A because they are the ones which is going to come in the upfield region. Now, when you take a look into this CH3 is connected to an oxygen, which is more electron withdrawing than carbon. So therefore, this is assigned B, right? When you compare the methyl protons with the methyne protons here, because this is a methyne proton, right? So obviously, you can see that it is downfield, and therefore, this has been assigned C, right? This is the one that's going to come in the more downfield region. So within the same environment, the order of the chemical shift is going to be preserved.